same as doing the Gaussian elimination. However, we want to store the M multipliers that we have calculated, and then also store the upper triangular matrix, right? So if we do that, essentially store the multipliers in a matrix called L, which is a lower triangular matrix, then the product of the lower triangular matrix and upper triangular matrix is going to give you what is the original matrix A. That's what we said. And then somebody asked, can we do an example problem? So because we essentially have proved this for I less than J, and then I said this is also can be provable for I greater than or equal to J, right? We have looked at a matrix where we had 1 0 0 0, and then you had M 2 1 1 0, and so on, right? So for that we have proved. So first let us look at before we look at how to come up with an algorithm for LU decomposition, let us look at essentially a small example problem. So we have an example here which I'll try to solve. We have matrix A is given by 1 1 minus 1, and then 1 2 minus 2, and then we have minus 2 1 1. Okay, that is A. And the right hand side B vector is given by 1 0 1. Okay, that's what we are given. Then essentially the idea is to now perform a Gaussian elimination, come up with the multipliers, and then convert this to an upper triangular form, and then use those multipliers and form them as a lower triangular matrix, multiply L and U, and then see whether you're getting A or not. Okay, that is the idea. So we know that the multipliers are basically M21 equals 1 upon 1, that is 1. Okay, similarly M31 is going to be minus 2 upon 1, that is minus 2. Then we can write R2 tends to R2 minus M21 R1, and then R3 tends to R3 minus M31 R1, right? Because first row is the pivot row here. Then if that is the case, I can now perform the row operations. The first row remains unchanged. So we have 1, 1, minus 1, and on right hand side I have 1. Okay. Then we have the second row, which is going to be just subtraction of the first row from the second row. That's going to be 1 minus 1 is 0, 2 minus 1 is 1. Minus 2 minus of minus 1 is going to be minus 1, and then 0 minus 1 is going to be minus 1, right? That's what I have. Then when it comes to the third row, we have minus 2, and then pivot row is the first row. So minus 2 minus of minus 2 times 1, that's going to be minus 2 plus 2, that is 0. Okay, and then we have 1 minus of minus 2, that's going to be 3, right? And then we have 1. Again, this is going to be 1 plus 2, but there is a minus in the front. So this is going to be 1 minus 2. This is going to be minus 1, is it? So this is going to be, we have 1, okay, minus of minus 2 times minus 1, right? This is going to be minus 2 times minus 1. So we have 1, is this correct? For this one, we have 1 minus of minus 2 plus 2, that is 3. Okay, yeah, so this is going to be 1 minus of minus 2 times minus 1. This is going to be minus 1. Okay, so that's going to be minus 1. And then on the right hand side, we have 1 0 1. So this is going to be 1 minus 2 times or plus 2 times 1. That's going to be 3. Okay, so this is going to be 3 again, right? Because I have 1 minus of minus 2 times 1. Okay, that's 1 plus 2, 3. Okay, so that's the after the first row operation. Then I can do calculate one more multiplier. Now the pivot row is R2. Then my pivot element is 1. Of course, here I'm not doing any partial pivoting, because if I do partial pivoting, I have to move this row to the previous row, because we said we want to keep the this one as large as possible. Okay, I'm not doing any pivoting. Then we have M32 is going to be 3 upon 1, right? That is equal to 3. Then my row operation is R3 tends to R3 minus M32 R2. Okay, so if that is the case, my matrix is going to be 1 1 minus 1 1. Then the second row also remains the same, 0 1 minus 1 1. And then the third row we have 0. Then this is going to be 3 minus 3, that is also 0. And we have minus 1 plus 3, right? That's going to be 2. Okay. Then we have 3 plus 3, that's going to be 6. Okay, so that is what we have. So as you can see, we have already transformed our matrix into an upper triangular matrix. I can, of course, now solve for this. If I solve for this, I'm going to get 2 times z equals 6. That is going to be z equals 3. Then we have y minus z equals minus 1. That means y equals minus 1 plus z. That means y equals 2. Then we have x plus y minus z equals 1. That means x equals 1 minus y plus z. That's going to be 1 minus 2 plus 3. That's going to be 2. Okay, so the solution to this problem is x, y, z equals 2, 2, and 3. Okay, so we can verify this by substituting, by multiplying this matrix, whatever we have, 1, 1, minus 1. With this thing, we should get the 1, 0, 1. Okay, so let us just verify quickly. So what we have is original matrix is 1, 1, minus 1, 1, 2, minus 2, then minus 2, 1, 1. Okay, then we have 2, 2, 3. So what does it give you? It gives you 2 plus 2, 4, minus 3, that's 1. Then you have 2 plus 4, 6, 6 minus 6, 0. Then we have minus 4 plus 2 minus 2 plus 3, 1. Okay, so that basically gives you Ax equal to B. So this is the solution. Now, let me formulate my lower triangular matrix. Lower triangular matrix is 1, 0, 0. My M21 was how much? M21 was 1 and M31 was minus 2. So that is 1 and minus 2. And this is going to be 1. And then M32 was 3, right? That's what we have calculated. This was 3. Okay, so this is 3. This is 0. This is 1. And then my upper triangular matrix is basically whatever I have found here. This is the upper triangular matrix, which is 1, 1, minus 1, right? So my U is 1, 1, minus 1, same as before. Then the second row is 0, 1, minus 1, 0, 1, minus 1. And then the third row is 0, 0, 2. Okay, that is what we have, 0, 0, 2. Okay, so I can multiply now this thing. So this should basically give me, so 1, 0, 0 by 1, 0, 0, that is 1. 1, 0, 0 by this one is 1. This is minus 1. This is going to be 1, 1, 1. This is going to be 2. Then we have minus 1, minus 1, minus 2. And then we have minus 2, minus 2 plus 3, 1. And then you have 2, minus 3, minus 1 plus 2. That is 1. Okay, so we have obtained the original matrix, that is A. Okay, so now we have kind of numerically proved for a simple 3 by 3 example that this indeed kind of works. That we can use LU matrices. That means whenever we are given a matrix A, we can decompose into L times U, because that way we can solve this problem for different right-hand side vectors, right? For different right-hand side vectors, we can solve for this without doing this, calculating this multipliers over and over again. Okay, so questions on this so far? Algorithm. So one way is to use the Gaussian elimination and store all the variables. The other way is to directly come up with an algorithm where we can calculate from the matrix product, we can calculate what are these quantities, right? So so essentially now I know that there is a particular pattern. I have my lower triangular matrix has all ones here, and then it has some non-zero elements in the lower triangular matrix, and my upper triangular matrix has non-zero elements along the diagonal as well as on the upper triangular part. So I'm going to denote my lower triangular matrix to look like this. It basically has ones, and then it has some L's or alphas, and then similarly my upper triangular matrix is going to be either it has U's or betas. Okay, that means I'm going to define my L and U as the L matrix as 1, 0, 0. I'm going to again take a 3 by 3 example. With this, we are going to build the algorithm. Okay, and then we have alpha 2, 1, alpha 3, 1. This is second row, first column. And then we have 1, 0. Then we have alpha 3, 2, 1. Okay, so that is what I have. Then my upper triangular matrix, I'm going to denote using betas. Beta 1, 1, beta 1, 2, beta 1, 3, 0, beta 2, 2, beta 3 3 0 0. Sorry, this should be beta 2 3. And then beta 3 3. Okay, so that's what I have. And then the product of this should basically give me some matrix that is A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, that's what we have. So yeah, so then what we want to do is that we want to derive a small algorithm from this small 3 by 3 matrix. We want to come up with a general algorithm where we can calculate what are alphas and betas in an allele decomposition in general. Okay, that's what we want to do. So for that, let me first multiply with the first row with the first column. So let me take the first column here. Okay, so I'm going to multiply the first row with the first column, then the second row with the first column, and the third row with the first column. That's going to give me basically beta 11100 times beta 1100 is going to give me equals A11, right? That's what I have. Then the second row when multiplied with the first column is going to give me alpha 21 beta 11 plus 1 times 0 equals A21. Similarly, when I multiply with the third row with the first column, that's going to give me alpha 31 beta 11 equals A31. Okay, that's what we have. Now, similarly, let me multiply all the three rows with the second column. Okay, so that means I'm going to do for the second column. So this is multiplying with the second column. That's going to give me 100 times beta 12 is beta 12 equals A12. Right? When you multiply with this, you're going to get this element, right? We're going to get this element. Similarly, when I multiply with the second row, I'm going to get alpha 21 beta 12 plus beta 22 equals A22. Okay. Similarly, when I multiply with the third row, I'm going to get alpha 31 beta 12, right? This is going to be alpha 31 beta 12 plus alpha 32 beta 22 equals A32. Okay, that's what I have. This is going to be equal to that. Okay. Similarly, let me multiply all the three rows with the third column. That's going to give me values in the third column of the original matrix. Okay, that is going to be beta 13 equals A13, and then I have alpha 21 beta 13 plus beta 23 equals A23. Similarly, I have alpha 31 beta 13 plus alpha 32 beta 23 equals, oh sorry, plus beta 33, right? I have plus beta 33 equals A33. Okay, is that correct? Everybody is able to follow? We just did a matrix multiplication for this problem. Now the thing is, I know, of course, what is my A matrix. I know all these entries. Now the question is, I don't know what are alphas and betas, right? That is what I want to calculate. I don't know what is alphas and betas. This is what I want to calculate from this algorithm, right? Okay. So if that is the case, then how do I go about calculating them? Let me take this first row, first column value. So from here I can calculate what is beta 11, right? Beta 11 equals A11. Beta 11 equals A11. Once I know beta 11, I can use it here and calculate what is alpha 21. So alpha 21 equals A21 upon beta 11. I just calculated beta 11 here. I'm using it here and then calculating this thing because I know what is all the three values. I already obtained what are the values of beta 11. I already obtained what is beta 11, alpha 21, and alpha 31. These are already calculated. Then let me go to the second column values. Here I know what is directly beta 12 equals A12. I know now what is beta 12. I just calculated here. I have also calculated alpha 21 in the previous column here, right? So I know this value. So I can calculate what is beta 22 from here as A22 minus alpha 21 beta 12, right? I can calculate B22. But then I have already calculated what is beta 12. I have already calculated alpha 31 from here. Alpha beta 22 also I have just calculated in the step above. A32 I know, so I can calculate what is alpha 32. I can say alpha 32 equals from here. Alpha 32 is going to be A32 minus alpha 31 beta 12 divided by beta 22, right? That means after this step, I have calculated beta 1, 2, beta 2, 2, alpha 3, 2. So I have calculated now what is beta 1, 2, beta 2, 2, and then alpha 3, 2, right? That's what I have calculated. Then I can go to the third column and calculate what is beta 1, 3. Beta 1, 3 is already available, that is A13. So then I can use beta 1, 3 and alpha 2, 1 that I have calculated here to calculate beta 2, 3. So my beta 2, 3 is going to be A23 minus alpha 2, 1, beta 1, 3, right? So I have calculated now this one. Once I know beta 2, 3, I know what is beta 2, 3. Alpha 3, 2, I have already calculated here in the previous step, right? Then beta 1, 3, I know, I calculated here. Alpha 3, 1, I calculate. I can calculate what is beta 3, 3. Beta 3, 3 equals A33 minus alpha 3, 1, beta 1, 3 minus alpha 3, 2, beta 2, 3. Okay, that means I calculated beta 1, 3, 2, 3, and 3, 3. So I can go back here. So I finished calculating everything. So beta 1, 3, beta 2, 3, beta 3, 3. So I have now calculated all the values of alpha and betas. Now it's a matter of putting these values back into a lower triangular matrix and an upper triangular matrix, which is going to be there, which is going to be the decomposition. Okay, so this sounds much simpler than what we have done before in terms of the multipliers, right? Because we are simply making use of the matrix product. Product of the two matrices. Now from here, can we build a general algorithm? For example, can I build now? Now, if you look at the way we have calculated, the way we have calculated is that I calculated beta 1, 1 first, right? And then we calculated alpha 2, 1, alpha 3, 1. That means we are coming in the column. Once I calculate this, I'm calculating this and this. Then we go to the next column, calculate this, and then calculate alpha 3, 2. Then we calculate this one, and there are nothing in alphas to be calculated. So we are going column by column. That means our j is running from 1 to n, right? J is running from 1 to n. My I is running from also 1 to n. But when I is less than j, I have beta values, right? If my j is 1, I only has 1 for beta 1, 1. If my j is 2, I can go to beta 1 to beta 2, 2. That means I will always be less than j to give me beta values. And I will always be greater than j till n to give me alpha values. If my j equals 1, I'm going to go from 2, 3 all the way to n. Similarly, if my j equals 2, I'm going to go from 3, 4, 5, and so on all the way to n. So that means we know that the beta values run from for beta values, I runs from 1 to j. For alpha values, I runs from j plus 1 to n, right? That's what we know, right? Because that is the columns as we see a pattern from here. Now, with that in mind, let us try to write a general expression for calculating betas. For example, if you look at beta 2, 3, right? Beta 2, 3 is equal to A23 minus alpha 2, 1, beta 1, 3, okay? That means we are subtracting the previous values, whatever is there. Similarly, beta 3, 3, there are two such subtractions. That means if I go for, in general, to ij, there will be many more such subtractions. That means if I were to write beta ij, that is going to be equal to aij, right? That is going to be aij minus alpha I. You can see here what you have for 2, 3, we have 2, 1, 1, 3. That means alpha I, sum k, beta k, j, right? This 2 and 3 are now applied on first and last indices of alpha and beta. Similarly, you have 3, 3, 3, 3 here, but then this index is going from either 1 or 2, right? That means here k runs from, as you can see, it is equal to 1 less than I. Like if it is 2, we are having 1. If it is 3, it is okay, so that is what my value of beta is. That means if I can sum up all the I minus 1 products like this, that's going to give me what is beta ij. Okay, so I can calculate like this. Similarly, I can also calculate my alpha ij. Alpha ij, I can calculate. Alpha ij would be equal to, let's say, look at this expression. This is going to be a ij minus, as you can see, I have only one value that is subtracted, right? But that is because we have, again, just like 3, 2 is applied on I and j here, but then this is similar to I alpha ik beta kj, right? If you want to calculate alpha ij, we are sending this ik kj, where k is running from 2 j minus 1. If 3, 2 is there, this is running from j minus 1. Unfortunately, I don't have a bigger 4, 3 or something like that to show multiple things. But then you will appreciate that this term is going to be, it is one just because it is only one term because we have 3, 2. If I had written this for 4, 3 or something, there would have been 2 terms here, just like what we had for beta. Okay. So that means this is going to be sigma alpha ik beta kj, where k runs from 1 to j minus 1. And then we need to also divide this with beta 2, 2. That means we need to divide this beta jj. Okay. So that is the general algorithm I have. Of course, here, again, we know that j runs from 1 to n, right? And then this particular one is valid for I less than or equal to j, and this is valid for I greater than j to or I equal to j plus 1 to m. I can even say like that, right? I goes from j plus 1 all the way to n, right? For this one. Or else I greater than j and less than n. So that means j is less than I is less than or equal to n, right? That's what we can write. Okay, is this clear? The way we build the alpha ij, beta ij, is this part clear?
Sir?
Yeah, go ahead.
Sir, just one question. So alphas and betas, we can, instead of them being dependent on each other, can we already make them based on just A's or Aij, so that, for example, in the left hand side, B11 beta 11 equal to A11. So when you next time when you write alpha 21, can you scroll a little bit down?
Yeah.
So alpha 21, instead of writing A21, replace, yeah, exactly. So that we get rid of beta 11. With this, maybe it might be easier to come up with an expression, or?
Sure. So I got your point. Yeah. So the thing is that now what you're saying is correct. I mean, I have just kept more variables here. So what you say is that I already have 9 variables here. Can I not use existing variables instead of using alphas and betas? You are perfectly correct. In fact, in an LU decomposition, what we see is that we have, if you look at the number of betas and number of alphas, if you put them together, they're exactly equal to 9, right? Whatever we have here, because betas are on the diagonal. So along the diagonal, they are taken, and then above the diagonal is here, and then below the diagonal, except for these ones, right? So in fact, we don't even have to write them as alphas and betas. We can even replace all alphas and betas with A values itself, because we are not going to reuse that value later. Okay, so as a result, we can replace them with A's itself. So that means the matrix A can itself be replaced. That means end of the process, your A matrix, once it is transformed into LU decomposition, is going to look like beta 11, beta 12, beta 13, alpha 21, beta 22, beta 23, alpha 31, alpha 32, and beta 33. Okay, that is how it's going to look like. This is nothing but your A values which were originally there. That means you can still make use of your A's to calculate all of them. So in that sense, it doesn't matter whether although I'm going to write it as BJJ, I can always write this as AJJ. Okay.
Understood, yes.
That is exactly possible. So only problem with this approach is that now I'm giving you some matrix, you're taking that matrix, but then end of that process, your A matrix is now transformed. You lost your original A. So if you need that A for some other and betas, which is basically one more copy of A, that's all, right? It is not a lot of memory, but if we don't need it, we can always delete that. But then we can work with the A matrix elements also themselves itself without allocating new memory also. So I can say there is no need for allocating new memory, right? This can be, the LU decomposition can be done within the memory of A itself, right? Once you have this thing, we have the LU decomposition. Only thing we need to be careful is that I can't compute these betas and alphas in any manner. I have to first calculate, as you have seen before, we have to first calculate for j equals 1. I need to calculate all the betas and alphas that fall in that column, then go to j equals 2, then calculate all the betas and alphas, then go to j equals 3, and so on, right? Only then this algorithm works. Otherwise, it's going to not work because it's going to make use of the previous values. So if we are using A itself to store, then it's going to use something else. That means for every j, calculate all beta ij's and all alpha ij's. That means calculate beta ij and alpha ij. Calculate beta and alpha ij for each j, and then go to next j value. Okay. That means for one j, we're going to calculate for all I, whatever betas and alphas we're going to get, then go to next j and then calculate all alphas and betas for all I, and so on. Only then this algorithm will work. Otherwise, it's not going to work, right? Because either we're going to make use of zeros, which is new alpha betas, or previous A values. Okay. Okay, other questions? Okay, no other questions. Okay, then what am I going to do? I mean, I have the A matrix that is written like this, which is also same as A equals LU, right? So we have this decomposition. Then as we discussed yesterday, if we want to solve for AX equal to B, then we're going to replace this A with LU times X equals B. We're going to call this U times X as some other vector Y. Okay, then I'm going to write Ly equals B as the first problem. Then we solve for what is Y from here. Once I know Y, then I'm going to solve for U times X equals Y. I'm going to solve for X, right? That means initially I started off the problem saying I want to calculate X. Now that X is obtained here, okay, by simply doing Ly equals B and then Ux equals Y. Okay. This is the forward substitution, and then this is the backward substitution. Okay, so we have these two. So forward substitution is equivalent to essentially doing operations on the right hand side, right? So in Gaussian elimination, we were doing eliminations not only on the A matrix but also on the B matrix. That is what this is equivalent to, right? We are doing forward substitution is equivalent to doing row operations on the right hand side matrix, which is exactly the same. Then this is the backward substitution, which was already there in the Gaussian elimination process itself. Okay, so that was already there. Okay, so that is the idea. Now that means now once you have LU decomposition of a matrix, you can calculate. You can compute X for several B vectors, right? Without actually doing the decomposition again. Okay, that's what we can do. That is the idea, which is basically an alternate form of Gaussian elimination. Okay. Any more questions before I go forward to write some small pseudocode for this?
Sir, one question, sir.
Yeah.
Sir, in the first step, we have been defining this L vector, no, sir? Like
L matrix, yeah.
Yeah, in that you are defining the diagonal as 1, 1, 1.
Correct.
Is that necessarily that you should be 1, 1, 1 to consider this whole code, or if it is something like other variable for I mean like other value apart from 1, then it will become 2 unknowns in our
Now, how many values do I know? For example, if this matrix was n by n, I have number of unknowns is n square, right? So I have only a number of known values is n square. I cannot, so that I can only make up n square equations here. I cannot make up more unknowns than the equations I have. I have only n square equations. So either, so if I put ones here, and then I write it this way, for example, let us say this is a 3 by 3 matrix. So I have basically 9 equations that I can form. So I can only afford to have 9 unknowns. So that means once I put ones here, I have 3 unknowns here, and I have essentially 6 unknowns here, right? So total I have only 9 unknowns. The alternate way is to put alphas here. For example, I can write alpha 1, 1, alpha 2, 2, alpha 3, 3, in which case I have to change this to 1, 1, and 1. In which case, again, I have 6 unknowns here and 3 unknowns here, right? And then total, I have only 9 unknowns. So 9 equations, when I multiply these things, I have 9 equations and 9 values that known on the right-hand side. So that is by design. Otherwise, if you're going to keep both alpha 1, 1, alpha 2, 2, alpha 3, 3 along the diagonal, and also beta 1, 1, beta 2, 2, and beta 3, 3 along the diagonal, then what you have done inadvertently is basically you have created how many unknowns? You have created n square plus n unknowns, right? You have created n square plus n unknowns, which is basically, this is going to be 3 plus 3, 6 plus 3 plus 3, 6. That is 12 unknowns, right? That is 9 plus 3, 12 unknowns. So n square plus n, which are too many unknowns. You only have 9 equations, right? Because you can only multiply these two matrices to get all the values that you have. So as a result, you should not do that. Either you have to put ones for either the upper triangular matrix or for the lower triangular matrix. And if you are going to put ones for the lower triangular matrix, that's a good question. That means if you're going to keep your alpha II equal to 1, okay, that particular algorithm is called Doolittle's algorithm. But if you're going to say, I'm not going to keep beta alpha I1, but I want to keep beta I1, that is called the Crowd's algorithm. Okay, that is called the Crowd's algorithm. So both are essentially the same. Okay, these are the same in terms of number of operations and the result, everything. Okay, the same result. They give the same result. So it's a matter of convenience how you want to put it. So, but both are possible. But keeping unknowns other than 1 along diagonals for both of them is not correct, because that is already creating trouble, because it's going to create more unknowns than you can solve. Okay, does it answer your question?
Yes, sir. Yes, sir.
Okay, good. Yeah. Any other questions, anybody? Okay, if there are no questions, let's go on to write a pseudocode for LU decomposition. So essentially, I'm now looping over J value. So do J equals 1 to n, right? That's what I'm looping over. Then do I equals 1 to J, right? When I go from 1 to J, I am first calculating beta values, right? Because my beta values go from, if I fix J equals 1, my beta goes from 1 to 1. If I fix J equals 2, my beta goes from 1 and 2, and so on, right? So I calculate what is beta ij. Beta ij equals aij minus alpha ik beta kj, k equals 1 to I minus 1. So that is what I have been given. So I'm going to say my beta ij is going to be, so I can assign this value, beta ij equals a of ij, that is the first element. Then I have to subtract off so many elements, that is the product of alpha ik and beta kj, and which has to run over k. That means I'll have another loop, do k equals 1 to I minus 1, right? That's what I have. Okay. And then I would write beta ij equals beta ij minus alpha ik star beta kj. Okay. Now you notice that if I'm looking at the first element, then I equals 1, j equals 1, I equals 1 to 1, 1. Then my beta 1, 1 equals a1, 1, and I'm not going to enter this loop because this is going from 1 to 0, right? So it's not going to subtract anything. Only from the second element onwards, it's going to enter this loop. So that means this basically takes care of only for this one onwards, it's going to subtract, right? Otherwise, this is going to be just a1, 1. Fine. Then what I have is that I have for alpha ij, I have aij minus alpha ik beta kj. K runs from 1 to j minus 1 divided by beta jj. Okay, that's what I have. So then essentially we finished calculating this, okay, betas. Then we will close this also. That basically finishes calculation of all the betas for that column, right? For the first column, we only have to calculate one beta. For the second column, we have to calculate two betas. For the nth column, we have to calculate n betas. That is consistent with this. Okay, then once I'm done with the first column, well, I'm not yet done. I'm done with the first column for calculating betas. But then as we have written the algorithm, we realize that we have to do beta calculations and all other alphas that come up in the same column. That means now I have to complete this I indexing. I went from I goes from 1 to j, then I also goes from do I goes from j plus 1 to n, right? I have to go to the remaining things. Then my alpha ij is going to be aij, okay? That is my I loop. Then I would again have a k loop. Do k goes from 1 to j minus 1, right? If we go back to the what we have written, this was k goes from 1 to j minus 1 and alpha ik beta kj divided by beta jj. So this is going to be alpha ij equals alpha ij minus minus alpha ik star beta kj, okay, and do. So that's going to stop, that's going to subtract all the elements. Then once I'm done this thing, I have to also divide this alpha ij with beta jj that is there in the denominator. And then I'm going to do and do. That's going to calculate all the alpha values. That means for j equals 1, it would have calculated 2 to n. That means if n was 3, it would have calculated for 2 and 3. It would have calculated alpha 2, 3, alpha I equals 2, 1, and then 3, 1, right? It would have calculated these two. And then I have to also close the outer loop, which is the j loop, right? So that also I have to close. That means I would do and do. This is closing the j loop. Okay, that is the j loop. Fine. So this way we're going to calculate all the betas and alphas that come in one column, then we go to the next column and so on. Fine. Is it clear, everybody? Okay, let me keep it here. Yeah. Questions?
So now we did for let's say 3 cross 3. So
Yeah.
when this size increases, maybe there can be new let's say conditions or some things which might get added. For example, now if you see some elements did not have I mean some positions did not have to if you scroll up
Subtractions, huh?
yes exactly.
No, that is not a problem. Okay, tell me.
Because for let's say beta 1 2 has only one direct value, but then when you go to beta 2 2 we have two components. 3 2 has let's say 3 components or so. So will this lead to when we have higher matrices of higher degrees, will we come up with some from new terms which are not really there initially, but then appear only after you cross a certain point?
No, it's not going to be a problem because we have written the general algorithm. Although, we have not written, because if this was 4 by 4, we would have had more terms that would come up here. Otherwise, we would not have got it. Okay, one way to, so it's not going to be a problem. Even let us take beta 1, 2. That means we are looking at j equals 2. Okay, so let's go back and see what this is going to do. So j equals 2. So we say j equals 2. I is going to run from 1 to 2, right? I is going to run from 1 to 2. That means I equals 1. It's going to calculate what is beta 1, 2, right? It's going to calculate what is beta 1, 2 equals a1, 2. Because I equals 1, this is going to be 0, right? So it's not going to go into go. So beta 1, 2 will be equal to a1, 2. Whatever is the statement that we have here, that is there. But for everything else, it's going to include these subtractions as we have written. Now, one way to look at this thing is, I mean, I have said that this index is going from to I minus 1 or j minus 1. So for that, I said if you look at the 2, we know that it is going from to j minus 1, right? Because 2 is the j value, it's going from j minus 1. The other way to think about it is alpha 32, if you take, alpha 32 is occurring here, right? Alpha 32 is occurring here. That means you're trying to calculate alpha value, which is for this column in this particular row, right? Then the alpha 32 will have subtractions from its predecessor values. The predecessor values, because this is the second column, will be only first column and so on, right? That means if this was some jth column, then these would have been up to j minus 1th column, right? That's why this went as sigma in the alpha calculation. We had j minus 1 here. Okay. Similarly, if you look at betas, we have let's take this beta 23. We have alpha 21, beta 13. I said essentially this is ij, this is ik, kj, but then this k, on what index this should run, right? We said because in this is 1, it is running from I minus 1, but then intuitively, or if you go back to the algorithm, beta 23 we are trying to calculate. Beta 23 is this value, right? Beta 23 is this value. Then it is going to have, when you multiply some row with this column, beta 23 is going to have beta 13. That means if this is the ith column, ith row, then it's going to have all the elements up to I minus 1, which are multiplied with the alpha values, and then it will go to the right hand side to be subtracted. Right? Is it clear, that part?
Yeah.
So that's what we are determining. And then there is nothing, there is no new surprise that comes here. It's just that we are able to do this because from the 3 by 3 example, even if you have taken 5 by 5 example or something, you're going to get the same pattern. Okay, so we're going to test that. So as far as this matrix is well behaved, and as long as we stick to either the Doolittle's algorithm or the Krauts algorithm, we are going to have the same calculations for alphas and betas. Okay, it's not going to be different. So this will work for even for any n by n size in general. Okay. More questions? Anybody on the pseudocode or anything like that?
Another way to put the question, so with the 2x2 matrix, would it be possible to arrive at this pseudocode?
It may not be, because 2 by 2 is too small. The thing is that you may not get the subtracting thing easily in the 2 by 2 code. Because 2 by 2 you only have these two and these two. Yeah. You may get it for one of them, right? When you calculate beta 22, you might get it, but not for alphas, I think, right? Yeah. So in that sense, you may not. It is not generic enough to derive a code, a pattern from there. I mean, we are trying to look at a pattern and then trying to generalize it. Now, also again in this case, as you see, I have kind of selected beta 23 and alpha 23 examples, or alpha 32 examples to write the pattern, because that's where you have a difference in I and j values. Otherwise, we will not be able to determine. If it is 3, we won't be able to determine whether this is k is actually running on I or j, right? So I kind of looked at only different numbers for ij to look at what are the values that will be subtracted from here. Okay. Yeah. I think that is either you can think of it like that, or by looking at the row or the column. When you look at beta some column, then the previous beta values up to that row will also be subtracted. If you're looking at alpha, then we know that all the values of alpha before that column will get subtracted. That means alpha goes as j minus 1, whereas beta goes as I minus 1, which will be subtracted. Yeah. Okay, any other questions, anybody?
Sir, in exams, how the questions will be asked, whether the problems will be given or...
Yeah. We'll have problems also. So I'll give you some assignment 1 maybe soon, probably maybe next week or something. See, for example, I have done in yesterday's class this round of calculation, right? Something like that I may give in the assignment. You can practice. So we'll have hand calculations. And then maybe you'll also be able to comment on, it'll be all hand calculations, whatever you can do with your calculator. We don't have a computer programming exam, but then is going to consist of, so assignment will consist of two parts. There will be hand calculations, okay, which is basically small, that's a system that you have to use and calculate. And then you will also have some programming part. So in the, so the programming part, you would use either C, C++, Fortran, or I think all of you would be better off with MATLAB maybe, okay, in doing the assignments. And the programming part is not going to be tested again in the final exam. So it's that you should get all the required programming concepts and doubts cleared in the while you do the assignments themselves. Whereas the hand calculation part is important because this is what is going to be useful to you in preparation for the exam, because the exam will be full of hand calculations or derivations or something like this, like what we are trying to do, following a similar pattern. So that is not an issue. So
Okay,
I think
sure.
the assignments will prepare you. Yeah.
In exams, whether the derivations will be asked similar to what we are
Similar to what we're doing. Yeah, some slight modifications of the derivations we are doing may be asked. Yes.
Okay, sir. Okay,
You will get
sure.
it as we go. Yeah, it is not going to be full of hand calculations. There will be hand calculations and derivations. So both will be there.
Okay,
Yeah.
sir. So,
Yeah.
so just
Go ahead.
just one request, sir. It's just if it is possible, if you can share us some one day before some brief what do you call some notes on on the next class. Not the complete one. At least we would be able to go through that and just to prepare for that for the class.
I
That
see.
would be
Okay.
yeah,
Okay.
we would be
So
yeah.
So I'm going to follow the same syllabus that I have given you. Maybe that one, or maybe I'll say a few words about what we're going to learn in the next class, right? In terms of
Sure.
what is the next thing, so that you can little bit prepare and come. That is better. So
Sure.
yeah. So maybe let us say tomorrow we're going to look at the operation count for the LU decomposition. Okay, and then we're going to look at the sparse matrices. Okay, how to solve sparse matrices. Specifically, we're going to look at this tridiagonal matrix solutions. Okay, that means if there are matrices where there are elements only along the diagonal and the subdiagonal and the superdiagonal, only along the three diagonals of the matrix, there are going to be non-zero elements. Everywhere else, it's going to be zeros. So that's kind of matrix is a sparse matrix and also known as a tridiagonal matrix. How to solve for tridiagonal matrices? Okay, because in engineering and in either FEM simulations, FEA or CFT, you're going to get these tridiagonal or banded matrices very often. So that's what we're going to look at next in the tomorrow's lecture. Okay, so I'll probably say something like this so that you can prepare and come. But this is also should be according to the syllabus as such. Okay. Then one more thing I want to say is that I think there are some efforts from the code office where you will be contacted for how to install MATLAB and get the VPN connection and so on. So once you have it, you'll have you can install MATLAB. I have also written some small sample codes for MATLAB, C, Fortran, and on. I'll probably show you for MATLAB because I think all of you are going to work with that one. We'll see some basic vector operations like calculating dot product between two vectors or calculating matrix multiplication, matrix addition, things like that in MATLAB. So those programs I'll share so that you can practice once you install it. Okay. So the thing is that now MATLAB is kind of very powerful. So you can actually solve all these things. For example, if you say LU decomposition, MATLAB can do it for you. If you say inverse of a matrix, it will do it for you. But the idea is that you will write these algorithms that we are learning, and then you will solve according to that algorithm. MATLAB might be using a different algorithm or something. But then, of course, because you have MATLAB handy, you can always compare your solution to what MATLAB is giving to check for your inaccuracies in the code or incorrectness and things like that. Okay, so that is the idea. Maybe sometime I'm going to show this, give you the MATLAB codes, or maybe show it to you maybe tomorrow if possible, and then give you the code so that whenever you install, you can start running them and then practice with that. Okay. Okay, any other questions?
Sir, can we get the last week class links and like
Sorry?
last week class links and what can we get it?
I think they're all uploaded on the course webpage.
Yeah, it is uploaded.
Sir, it is uploaded.
Yeah. All the lecture notes and the videos are there on the page. Yeah. course page. Yeah.
For the semester, I mean, in the previous exams, we were taking some formula sheet with us. Is it allowed?
Yeah, I think it should be okay. Yeah, you can come up with a formula sheet, not a problem.
Thanks a lot, sir. Thank you.
Yeah, it should be fine. I'll see if I think that should be fine. You can take a cheat sheet or something like, 1 page where you write whatever you want. That should be fine. Yeah, that should be perfectly fine.
Thank you, sir. Thanks a lot.
Yeah, be fine. Yeah. Okay, I'm going to stop here, guys. Thank you. Then I'll talk to you tomorrow. Okay.
Thank you, sir.
Thank you. Bye bye.
Thank you.